You have seen the mechanistic aspect of the radical reaction or halogenation. Now we're going to look into the thermodynamic aspect of this reaction. Right? Thermodynamics means that we look at energy and equilibrium. So energy change in the reaction. In terms of energy change, there are two types of reaction. We have exothermic reaction and an endothermic reaction. For the exothermic reaction, so the delta G is negative, and we call this type of reaction spontaneous. They can happen. All right? Doesn't need to supply extra energy into it. For the endothermic process, the product is less stable than the reactant. So if you want to convert the reactant to the product, we need a lot of energy to input into the reaction. Okay, so it's not spontaneous. All right, and so that's a thermodynamic aspect. So the rate aspect, which is kinetics, we talk about activation energy. So lower activation energy, the reaction go faster. Okay, this is review. All right, let's take a look right here. So to decide whether or not reaction will occur, we look at the delta G, which is Gibbs free energy. We want it to be negative. Okay, and the Gibbs free energy depends on two terms. So enthalpy, which is the energy associated with bond breaking, bond forming in the reaction, and the entropy term. This one associated with randomness of the molecule. All right. If you don't know what randomness is, I'm going to tell you in a bit. All right. Let's take a look at the reaction. So you start out with two molecules, and you end up with the two molecules, and all of them do the same thing: fluorination, chlorination, bromination, iodination. Start with two molecules, so alkane and a halogen, and you end up with two molecules. All right. So there's no change in randomness. The change in randomness will be you start with one molecules and you end up with two. That's when you increase the randomness. The thing just really get messy there. If you start with 10 molecules, you end up with one molecule. Thing doesn't kind of reverse, not get messy, right? So we have that's what we have negative entropy. Right? But this one you start with two, you end with two. Well, the entropy doesn't change. So delta S is zero. The whole term is zero. We don't talk about it today. So just forget about entropy. Which means that whether or not the halogenation will occur depends on this term. Right? Depends on this term, which is the bond energy. Energy with the bond, breaking or bond forming in the reaction. Right? So if this guy negative, the delta G is negative. If the enthalpy term is positive, the delta G will be positive, and that's non-spontaneous. We want this to be spontaneous, negative. Right? All right, we're going to take a look at the enthalpy term of each reaction here. Okay, so to conduct, let's say start with fluorination. To make a fluorination, you have to break this bond, CH bond and fluorine bond, and then make CF bond and HF bond. So we have bond breaking here and bond forming here. Okay, and we're gonna use do calculation in a bit. You don't have to. I'm just gonna do it. Just show you, and I want to explain a little bit more. So, but I have to show you this first. So how I get the number. So to look at bond forming, bond breaking. So on the left side, bond breaking. So we're trying to break CH bond, which is really strong one. Take a look, 435 kilojoule per mole. So I'm gonna add 435 kilojoule per mole right here. So break this bond. We also have to break a fluorine bond as well, which I need at least to supply 159 kilojoule per mole. So add these two in the reaction. So I have to add this energy total to start this reaction. And then when the reaction occurs, I'm going to get this back, gain this energy back. So CF bond forms. So CF bond is 456, really strong. So that's negative. That's what is coming out. And HF bond, with HF bond, 569 kilojoule per mole. So that's what I get back. So I input this energy input, and this is the energy output after the reaction occurs. Sum them up. That's the enthalpy of this reaction. And in this particular case, that is the Gibbs free energy. Okay, so the Gibbs free energy of this reaction is negative 431 kilojoule per mole. Is it spontaneous or non-spontaneous? Yeah, this is spontaneous. Fluorine love to alkane love to do fluorination because you get a lot of the Gibbs free energy is really negative, highly negative. Right? Compared to chlorination, bromination, and iodination, a little negative, even a little negative. What's going on with the iodination? It's positive, right? So this is the only reaction, a radical reaction that's not spontaneous. If you want this reaction to happen, you have to apply 55 kilojoule per mole. And how many moles are there in the solution? All right. A little bit problem right here. Go back to fluorination. It's so hard to say. Fluorination. The negative here is a big number. Apparently, it's really difficult to handle. It's too difficult. Put that in the flask in a certain amount. It produces large amount of heat. The glassware break. The machine to do the reaction broke. Just too much energy. It's too hard to handle in the laboratory. Maybe in the industrial level, they do handle fluorine, but not in the laboratory. All right. So in the laboratory, we're gonna talk about only chlorination and bromination. That energy, that's what we can handle. Okay. All right. We're gonna talk about the kinetics and radioselectivity of the chlorination and bromination. Not talk about fluorination. I can't say this word. Fluorination. Because it's produced too much energy, you can't handle it. Iodination is not spontaneous. Not talk about it. Just these two. All right.